Welcome, seekers of mathematical enlightenment. Today, we embark on a journey through the harmonious world of trigonometric integration.
Game, let us first have an activity. It is called Identity Review. All you have to do is choose the correct identity and you will be given 5 seconds to answer each question. So, let us start. For item number 1. The correct answer is letter A. Let us have the item number 2. Which of the following is the correct identity? A or B? The correct answer is letter A. For item number 3. The correct answer is letter B. For item number 4. The correct answer is letter B. And for the last item, which of the following is the correct identity? The correct answer is letter A.
I guess we are all now prepared to discuss more about trigonometric integration. So some integrals involving trigonometric functions can be evaluated using trigonometric identities. So we do have, as we have reviewed, we do have the Pythagorean identities and we also have the half-angle identity. No? And now, the trigonometric integrals involve trigonometric operations using trigonometric function, identity. Now, we apply these trigonometric identities to evaluate the integrals involving products of powers of trigonometric function. So, for today, we're going to discuss 4 cases of trigonometric integration. So, for the case 1, we do have the integral of sine raised to the power of n of x dx, or the integral of cosine raised to the power of nx dx is a positive odd integer. So, both the trigonometric function sine and cosine have a positive odd integer for us to apply the case 1 rule. So, how we're going to solve the case 1 rule? So, we do have this one. So, we have to factor out the a single sine x dx. Therefore, the integral of the sine raised to the power of nx dx is equal now to a integral of the quantity of sine raised to the power of n minus 1x, meaning the power of our trigonometric function is raised to the power of even integer, since we factor out a single sine of x dx. So, and then what we're going to do now is the integral of sine squared of x, quantity of it raised to the power of n minus 1 divided by 2. And we do have now the sine of x dx. After that, since sine squared of x has an identity, which is the Pythagorean identity, in which the sine squared of x equals to 1 minus cos squared of x raised to the power of n minus 1 over 2 multiplied to sine x dx. So, how about we apply this into the cosine raised to the power of n of x dx, where n is a positive odd integer. The same way as we applied it in the sign of x, you just have to factor out a single cos of x, and we have to integrate the cos squared of x, the quantity of it raised to the power of n minus 1 over 2, multiply the cos of x. So the cos squared of x do have an identity, which is the Pythagorean identity also, in which cos squared of x, cosine squared of x is 1 minus sine squared of x. The quantity of it, n minus 1 over 2 multiplied to cos x dx. Is that clear? Okay, so to furtherly understand this one, I'm gonna give you an example. So, for this one, we're going to integrate the cosine cube of x dx. So how we're going to apply this? So we can apply the case 1 since the power of the trigonometric function that we have is raised to the power of odd positive integer. So let's try to solve this one. So the integral of cosine cube of x dx equals to the integral of cosine squared of x multiplied to cos x dx. Since the cosine squared of x do have an identity, which is the 1 minus sine squared of x, so we are going to write the cosine squared of x into its identity. What we have here now is the integral of the quantity of 1 minus sine squared of x multiplied to the cos x dx. Next is that we are going to apply the u substitution. The u substitution is we're going to let u equals to sine of x, and du, derivative of sine x, is of course cos x dx. So after that, we apply the u substitution. So therefore, what we have now is the integral of 1 minus u squared, the quantity of it, du. And now, apply the trigonometric, the integrals rather. Now we have the integral of 1 du minus the integral of u squared du. So now we're going to apply the integration. What is the integral of 1 du? 1 du is, of course, u. So the integral of 1 minus u squared du is 1/3 u cubed. This is it. Substitute back the u equals sine x. And what we have now is sine x minus sine of x minus 1/3 sine cube of x plus c. Therefore, the integral of the cosine cube of x dx equals to sine x minus sine of x minus 1/3 of sine cube of x plus c. Do you have any clarifications? If not, let us proceed to talk about the case number 2 of the trigonometric integration. So for this case, we have to follow wherein the integral of the exponent of our function is raised to the power of positive integer, but the trigonometric function is sine of x and cosine of x. So we have here the case number 2 in which the integral of sine raised to the power of n of x multiplied to cosine raised to the power of m of x dx, where at least one of its exponent in which m or n is a positive odd integer. So what we're going to do this one is to factor out. What we're going to factor out here is the cos x dx. So our function will be equal to the integral of sine raised to the power of n of x multiplied to the cosine raised to the power of m minus 1, since we do cosine raised to the power of m minus 1 since we factor out the 1 cos of x dx, and multiply to the cos x dx in which the integral that we factored equals to the After that, no, the integral of it be equal to now to sine raised to the power of n of x multiplied to cos squared of x, the quantity of it raised to the power of m minus 1 over 2. So, multiply to cos x dx. Right after that, we will use the Pythagorean identity for the cos squared of x, since it has an identity which is the 1 minus sine squared of x raised to the power of m minus 1 over 2 multiplied to cos x dx. To furtherly understand this one, let's have the integral of sine x, the same for this one, but we're going to factor out the sine of x dx instead of the cos x. So what we have now is the integral of cosine n of x multiplied to sine raised to the power of m minus 1 of x and multiplied to sine x dx. Right after that, we're going to have the sine raised to the power of m minus 1x to be in the form of sine squared of x, the quantity of it raised to the power of m minus 1 all over 2. So what we have now is the integral of cosine of n of x minus the Pythagorean identity of it, of the sine squared of x, which is 1 minus cosine squared of x, the quantity of it raised to the power of m minus 1 all over 2 multiplied the sine x dx. So to furtherly understand this case number 2, I have here an example. So this example is, how about we integrate the integral of the sine raised to the power of 5 of x multiplied to cosine squared of x dx. So for this one, as you can see here, that the sine raised to the power of 5, the sine raised to the power of 5 of x is an odd integer, or the trigonometric function that we have for the exponent of the trigonometric function that we have for sine is an odd integer. That's why we have to factor out one of it, so that the one of it, so that we're going to have a sine function in which it is raised to a positive even integer. So what we have here now is the integral of the cosine squared of x multiplied to sine raised to the power of 4x multiplied to sine x dx. Right after that is we are going to rewrite the sine fourth of x, in which the trigonometric function of sine is in the form of squared. Let us see for the example now. So the integral will remain the cosine squared of x multiplied now to, from the sine raised to the power of 4 of x, we have now the quantity of sine squared of x raised to the power of 2 multiplied to sine x dx. Since the sine squared of x has a trigonometric Pythagorean identity, which is the 1 minus cos squared of x, we have now the integral of the quantity of 1 minus cos squared of x raised to the power of 2 multiplied to cosine squared of x multiplied to sine x dx. Right after that, we can now apply the u substitution. The u substitution is that we're going to let u be equal to cosine of x, and the derivative of the cosine of x is equal to negative sine x dx. What we have now is all of the cos x that we can see here can be written in a form of u. So we can apply the trigonometric integration easily, rather. So what we have now is the the negative, we factor out the negative from the negative sign x dx, so that we have now the negative of the integral of the quantity of 1 minus u squared raised to u squared equals to negative integral of 1 minus u squared raised to the power of 2 multiplied to u squared du. Right after that is that we have to expand this, which is the 1 minus u raised to the power of 2. So we expand this into the form of 1 minus 2u squared plus u raised to the power of 4. So we still have the u squared du. So right after that, we distribute the u squared to the trinomial function that we have right here. So what we have now is the negative integral of the quantity of u squared minus 2 u raised to the power of 4, because u squared times u squared equals to u4 raised to the power of 4 plus u raised to the power of 6, since u raised to the power of 4 multiplied to u raised to the power of 2 equals to u raised to the power of 6, and we do have now the du. So this one, we can easily now apply the integration. So the integral of the u squared equals to 1 over 3 u cube minus, what is the integral of 2u raised to the power of 4 equals to 2 over 5 u raised to the power of 5. And what is the integral of u raised to the power of 6 is 1 over 7 u raised to the power of 7 plus c. Let us not forget the plus c and the negative sign that we have earlier. So right after that, we can now substitute back the cosine of x to every u that we can see in our integrated function. So what we have now is negative. We also have to distribute also the negative sign that is outside of our grouping symbol. Now we have the negative 1/3 cosine of cosine cube of x plus 2/5 cosine raised to the power of 5x plus 1/7 cosine raised to the power of 7x plus c. Therefore, we already solved the example number 2, in which the integral of sine raised to the power of 5 multiplied to cos squared of x dx is equal to negative 1/3 cos cube of x plus 2/5 cosine raised to the power of 5x plus 1/7 cosine raised to the power of 7 plus 7x plus c. Do you have any questions, clarifications, or violent reactions? If none, let us proceed to the case number 3. So the case number 3 states us that what if the integral of our sine and cosine, or thus the integral of sine raised to the power of n of x and cosine raised to the power of m of x dx, where both m and m are positive even integer. What we have now here is we're going to factor out. So I have here the procedure. So the integral, let's say for example, the integral of sine raised to the power of n of x dx. Now what we have now is to rewrite the sine squared of x in the form of this raised to the power of n minus 1 over 2. So after this one, if our function is our trigonometric function sine and cosine both have m and n, that their power is a positive even integer, what we have going to apply is the half angle identity, in which the half angle identity of our sine squared of x equals to 1 minus cosine 2x all over 2. Let's say for example that we want to know for the cosine of n x dx. So for this one, we still going to apply the half angle identity in which the cos squared of x equals to 1 plus cos sine 2 of 2x all over 2. So what if that the both of the sine and cosine are both in a one function and their power are both also positive even integers. So what we're going to do now is also apply the both half angle identity for them. So let's say for example that the integral of sine raised to the power of n of x dx multiplied to cosine raised to the power of n of x dx. So we are going to write the sine raised to the power of n dx be equal to the quantity of sine squared of x n minus 1 all over 2 multiplied to the cos of cosine m of x dx, which is be written as now to become cosine squared of x, the quantity of it raised to the power of m minus 1 over 2. So we apply for the sine squared of x and cos squared of x in the half angle identity, which is projected right here. So to furtherly understand what I am saying regarding the case number 3 in which the sine of x dx and the cosine of n dx, or the sine raised to the power of n of x times cos raised to the power of m of x dx, where both m and n are positive integers. So let us have an example. So this one is very easy example. Let's say for example that the integral of sine squared of x dx. So as you can see here that the function, the trigonometric function has a power raised to the power of 2. So we can apply the case number 3. So what we're going to apply here is the half angle identity. So the integral of sine squared of x dx equals to the integral of the half angle identity for the sine squared of x equals to 1 minus cosine 2x all over 2 dx. Right after that, we distribute the integration in which it will be written in a form of the integral of 1/2 dx minus the integral of cos 2x over 2 dx. So after that, we apply the u substitution again. So for this one, we are going to apply the u substitution for this function, the cosine 2 of x all over 2 dx, in which we let u be equal to 2x and du be equal to 2 dx. That's why we have the dx equals to du over 2. So after that, we apply now the u substitution. So we have now the integral of 1/2 u since we have now the 1/2 u since we integrated the 1/2 dx minus the integral of cosine u all over 2 multiplied to 1/2 du, in which the 1/2 du is d dx. No? Right after that, we factor out, or like we factor out the constant, which is 1/2 times 1/2 is 1/4. So we do have the 1/4 now of the integral of cosine of u du. So what is the integral of cosine u? We do have now the sine u. So what we have now is the 1/2 u minus the 1/4 sine of u plus c. So right after that, since we apply the u substitution, we substitute back the 2x. So what we have now is 1/2 times 2x minus 1/4 the sine of 2x plus c. So what we have now is x minus 1/4 sine 2 of x plus c. Do you have any questions, clarifications for the case number 3 of the trigonometric integration? Because now we are going to proceed to the case number 4. So if none, let us proceed to case number 4. So the case number 4 involves the trigonometric function such as the tan and the tangent rather and the cotangent. So that what we have here is the integral of tangent raised to the power of n of x dx, or the integral of the cotangent raised to the power of n of x dx, wherein n is a positive odd integer. This is like the case number 1, but it is the case number 4 is applied on the trigonometric functions such as the tangent and the cotangent. So what we're going to do now is, let's try to see now. What we're going to apply here now is the trigonometric identity of the tan squared of x, which is the second squared minus 1. So the integral of tangent raised to the power of, what we're going to do now is the integral of tan raised to the power of n of x What we're going to do now is the integral of tangent raised to the power of n of x dx be equal now to the integral of tan raised to the power of n of x multiplied to tan squared of x dx. So, right after that, no, we have now the integral of tan raised to the power of n minus 2 of x multiplied to the Pythagorean identity of the tangent squared of x, which is the second squared of x minus 1 dx. What about for the cotangent? So, cotangent can be solved in the form of this one. You have to follow the cotangent raised to the power of n of x equals to the integral of the quantity of the cotangent raised to the power of n minus 2 of x multiplied to the cotangent squared of x dx. Right after that, we apply the trigonometric identity for the cotangent of x dx. We have now the integral of the cotangent raised to the power of n minus 1 of x multiplied to the identity of cotangent squared of x, which is the cosecant squared of x minus 1 dx. So to furtherly understand the case number 4, I'm prepared to you an example rather. So the example for this one, what about the integral of tangent cube x dx? As you can see here that our function is, our trigonometric function is the tangent. Our trigonometric function is in tangent, and the exponent of our trigonometric function is a positive at integer. So it does satisfy the case number 4. That is right. So to solve this one, we have to factor out the tan of x dx from the tangent raised to the power of tangent cube x dx. So what we have now is the integral of tangent squared of x multiplied to tangent x rather dx. So right after that, we apply the Pythagorean identity, or the identity for the tan squared of x, which is the second squared of x minus 1, and remain the tan x dx. So right after this one, we can apply now the u substitution. So our u substitution, we let u rather be equal to tangent of x, and the derivative of course of our tangent of x equals to secant squared of x dx. So the integral now of tangent cube of x dx equals to the integral of the secant squared of x tangent of x dx minus the integral of tangent of x dx. Okay. What we have here now, since we apply the u substitution, we have the integral of u du minus the integral of u, or the integral of tan x. So what is the integral of u du? We have the 1/2 u raised u squared minus the integral of tan x. What is the integral of tan x? We have the negative ln cosine of x, the absolute value of it, no? Plus c. So after that, we substitute back the u equals to tan x. So our integrated function that we have now is the 1/2 tangent squared of x minus ln, or natural log absolute value of cosine of x plus c. Okay, I guess that's all for today. Thank you for listening. I hope you learned something. If you do have questions, clarification, kindly leave it in the comment box below.